Hello and welcome back to Source Dive, where we take an in-depth look at some of the most interesting low-level open source code bases out there, kind of try and get a sense of what makes them tick. We're currently looking at XV6. XV6 is a kind of learning operating system that's based on the original version 6 Unix, which was widely distributed, widely documented in a very famous book, and so basically this is for the RISC-V architecture, so there are some RISC-V specific things, and today we're going to actually be looking at one of the quite specific RISC-V things, although the general concept here does apply widely across different processors. Only like the kind of fine details are going to change. But just keep an eye on that and understand that even though pretty much the essentials of this will be the same, it may differ a little bit on x86, it may differ a little bit on ARM, may differ on some of the other architectures out there. Okay, so what we're actually looking at today is the virtual memory subsystem. Now, virtual memory, I think, is probably one of the more intimidating topics for people coming to operating systems, or like kind of like coming into this this thing. At least it was for me. Like when I started learning about this, and I'm self-taught in this, so I didn't learn this at university. But when I came into this, I kind of thought that virtual memory was a more complicated concept than it really is. And that, you know, while it's not strictly true to say that it isn't complicated, at least the essentials of it aren't. And you can certainly get a really good grasp on it. And the way that it's presented in XV6 is a pretty simple, straightforward implementation of what can be done. It hides away some of the details of like really modern operating systems and processes, but that doesn't really matter. Like what we're focused on is, you know, kind of getting an understanding of like, well, one, how this code is written and how it comes together, but also like what is the core essential idea of this. All right, so without further ado, let's kind of get started on it. And today is the first day, and I think we're going to be bringing in the specification document as well, at least one of them. So what I've got over here is the RISC-V Instruction Set Manual Volume 2, and the Volume 2 refers to all of the parts of the instruction set which are considered privileged. So this is everything that's to do with like machine mode, supervisor mode, hypervisor, which we won't talk about at all, but it's there in this document a little bit. And certainly, like, we're going to focus on some of the supervisor parts here, because actually how the virtual memory system works is described fully in this document. Okay, one question you might have right off the bat is, what even is virtual memory? Like, why is it important? We've touched on it a little bit in some of the previous episodes, but virtual memory is basically this idea that especially when you're running in a user process, so when you're not running in the kernel, right, you're running kind of, let's call it untrusted code, right? It's just like the user level code, stuff that you don't want to just clobber parts of the computer system. Anytime that like your program tries to access the next instruction or access some variable in memory or just do anything that's to do with memory, it doesn't have like a true like physical view of the memory. Like it doesn't like go and say, give me the thing at address hex 8 million and that's the first address in memory. No, instead it gets a view of memory which first has to be translated. So I've got some address. That address is essentially a key, and that key will go and tell us where the actual address is. Seems kind of complicated, and it kind of is, but there's a really good reason for it. I mean, there's several really good reasons for it, but like one of the main good reasons for it is to make sure that your process has just a very limited view of the world. One, it can assume that it is the only process on the system. That's quite an interesting thing, right? To this process, it looks like it has access to everything. And there are no other processes, and there are no places where if it accidentally writes to this piece of memory, it's going to clobber someone else's memory. That doesn't happen. So it's got a kind of restricted view where it thinks it's the only thing in the world running. And kind of, I guess this already touches on something that I already said, but because of like the implication of that is that it can't touch anyone else's memory. So it's not only about it having a view of the system, it's like everyone's got their own view of the system. Everyone feels like they are, equally important. However, all of the permissions and everything that's related to that user's view of the world is decided by the kernel, right? So each user process will have certain privileges to the memory, even the kind of view of the world that it's been given. So we can say to a user that's trying to access a certain place in memory, well, this memory will always only be readable. You can't write to it. You can't execute it. Or you can execute it and you can read it, but you can't write to it. And there are all kinds of security reasons you want to do things like that. But the core thing here is that the kernel can actually present a very kind of nuanced view to the process. And kind of third and kind of, I'm not sure if it's the most important, but it's certainly an important point in operating systems, is that the kernel can actually make use of this subsystem where we present each process with its own view of the world. We can make use of this and allow processes to actually talk to each other by actually creating a map to the same place in physical memory from two different places, two different processes. So although the processes can't directly access each other's memory, we can actually map some of the same physical memory to the same place. So they can actually communicate that way, right? They can communicate over a common piece of memory. So that is a really interesting thing that we can do. There are many, many interesting things that we can do, but these are kind of the most important. All right, so I'm going to show you a quick diagram because I think trying to get an understanding of like how this works is quite important. So let's pretend we are a user process for a second. Let's pretend we're a process. We go ask for the next instruction in memory, and we're saying that is at some arbitrary address. Like, here's my arbitrary address. That's where I'm supposed to get my next instruction. When that instruction comes to be executed, the processor in hardware, so this is not a software thing, this is not something the kernel needs to do, this happens in the CPU hardware. The CPU hardware will go and look into a certain register called the SATP register. And if we sort of go and look over in the spec here, we can actually go and find that register. So if we look in the supervisor CSRs, down here, this is the supervisor address translation and protection register. So this is a register that effectively holds the address of something called a page table. So going back to this diagram here, a page table is just a table of values, right? It's just like an array, even, you can think of it. It's just an array of addresses, effectively. Or not really addresses, but it's a sort of table of entries. There are sort of address-sized things inside each of these entries. They're called page table entries. So this address points at a page table. And what the processor does is it takes the address we've given it as the user process, like, hey, my next instruction's at this memory address, ABC. Take my address, and what happens here is the processor will then use this table to perform a series of lookups and eventually translate this address to the actual physical address that we can find that instruction in memory. So what happens is the address itself is not really just a single address, of course. We know it's called a virtual address. That virtual address is a kind of key that's made up of several parts. And we use one of those parts to go and like figure out which index inside this table we're looking at. Each of our page tables that we have 512 entries each. So what we do is we take a piece of our address and we use it to look up which one of these we're going to go and look for. Say we picked number 1, right? Then in that case, what we would do is this will essentially contain a pointer to another page table. And we go and use that pointer to look up the next page table entry. Let's go for this one. Let's say we were at 0 and go up here, because that way we'll see that we can make several jumps. So then there is actually then another part of the address that's used to look up a new entry in the next page table. So then we do that and we go here and we get one final level of page tables. So then we use a third piece of our address, our virtual address, to go and look up which page table we're in here, and eventually that will point us to an actual physical address. And not only does this contain an actual physical address, it actually also contains some other information that's used by the kernel to figure out what are the permissions of this page. What effectively of the address that we're translating, but of the page in general. So then essentially each of these entries, in every step here, each of these entries, it kind of looks like this. This is how you break it down in terms of the 64 bits that are used. So all the bits over here, these are used by the operating system and the CPU itself to decide like what this page is capable of. So is this valid? Is this a valid entry in this table? If it's not valid, then it's kind of like we eliminate that kind of that would be considered an error if we found our way to a page table entry that was invalid. That would be an error. Then we have is it readable? Is it writable? Is it executable? Is it a user mapped page? Because we do page address translation. We do virtual memory both in the kernel and in the user space. We'll see how that works in a little second. So is this a user page? And then this is a global flag that's used for something specific. We'll skip over it for now. And then there are 2 bits here which can be used as a mechanism for understanding like what the kind of state of this page is in terms of has it been written to or not. Then there are some bits that can be used by the kernel for general things, and then we have these 3 pieces of data here which are used eventually to construct, together with the last part of the virtual address, that are used to construct the physical address that we map to. So that's probably a lot to take in at the moment, and like I'm distilling this entire thing into a tiny image right now, so don't be alarmed if it doesn't make total sense right now. But this is the big picture actually, and what you can see here, kind of probably from this diagram, is that you can end up with a lot of page tables, right? We're not limited on like how many things we can map, right? Because we can point to 3 different levels of page tables at each moment having 512 possibilities. And this is per process. We have a lot of possibility to map memory this way. And we can map memory in all kinds of crazy arbitrary ways, because we can map some memory to the same place over and over again. We can map some memory to disparate regions. So an address that might be right next to each other in terms of virtual space could be completely far apart in physical space. So there is that whole thing. Okay, so that is the idea of page tables. That is the supervisor address translation and protection register. If we go back over here for a second, I'm not going to just sort of read the spec word for word, but basically there are this SATP register can be broken down into a physical page number, which is 44 bits. So this is 44 bits, which is not a complete address because it's pointing at a region of space. So we don't have to specify actually the full amount of bits. Then there is this ASID, which is used as a kind of further identification mechanism, which we can also use to then as for things to do with caching, which we won't go too much into now. I want to keep things like fairly simple in terms of the core concept of virtual memory for now, without going too far into things like caching, because it gets complex, of course, when you start taking all these different things into account. And then finally, there are 4 bits which are used to determine the mode. And the cool thing about RISC-V is that you actually can have different schemes of virtual memory. Like your processor, well, let's say RISC-V as a whole, as a specification, doesn't say specifically that each processor must do it this particular way. There are actually several different ways a processor can implement virtual memory. And that's kind of nice and flexible as compared with something like x86, where there is a single way this is done. It's done in a very similar way, but it's fixed, right? And if you want to change this at some point, like, it's not directly in the spec as of now, at least as far as I understand it. So then there is actually a section here that talks about or virtual memory. So let's say there are 3 different kinds of virtual memory systems. So there is SV32, which is for 32-bit memory systems. And there is a whole explanation of how things work. You can see we have a very similar piece of data to what I showed just now, showing physical page numbers and these bits. You can see that there are only 2 levels of translation for 32-bit, rather than 3 levels of page tables. Okay, but if we scroll down to SV39, this is a 39-bit paged memory system, and this is for 64-bit systems. So now at this point, virtual addresses, they look like this. So a virtual address is split into 3 pieces, 3 9-bit addresses. And if you think about that, 9 bits gives you 512 possibilities. So that's how we end up with our 512 entries. And then there is a 12-bit offset. So if you multiply that out, like by the number of bits, and which number you would get out there, 12 bits is 4K, 4096. And that's a number we've seen in the last episodes when we've looked at the kernel page allocator, and when we've looked at like stack and all of that kind of stuff. We've seen that there's this magic number of 4096 floating around all the time, and that is because that's the size of a page. So if you think about it, right, you actually only need to, when we don't like take individual addresses and give those like their own translation. We actually translate in blocks of 4K. So if you had to translate each address individually, that would take up a lot of memory. It would be a real problem. So instead what we do is we make a trade-off and we say, well, we're going to group things up into 4K chunks. And each of those 4K chunks will have the same permissions, the same read, write, execute, all of that kind of stuff. They will be the same. And you'll end up mapping your address. The top part of your address will map which of those 4K blocks you're in, and then the last part is your offset within that page. So that is kind of how that works in terms of this 4K offset. So yeah, what we end up doing, right, is we end up translating one of these virtual addresses into one of these physical addresses. And the physical address is broken up into 4 bits. I mean, we have the same page offset. This is what comes out of a... this is what we get out of having gone through our page table entry. Like, we've taken our page table entry, we kind of convert it to an address in this format, which kind of stacks up our physical page numbers that are part of this address, and we add our offset on the end here, and that gives us our actual address into memory. So one thing you'll notice is that we don't actually get full 64 bits out of this. We're actually cutting off some of our address space, but as it turns out, 55 bits is quite a lot, right? At least in our current systems of like everyday computing, 55 bits for memory, physical memory, is actually enough. And if you think about the fact that the user really only is interested in RAM, like the user is not doing anything directly with hardware, so the user doesn't need to map into physical hardware addresses, those 55 bits start to be quite reasonable, right? It's not that we need to cover the full space. Okay, so that's kind of the big picture. Let's try and take a look back at the code now and go back to where we were here in this main function. So we've covered all of the console booting up, and we covered the kinit, which deals with the physical page allocator. So we saw that basically we were taking everything from like where the kernel ends up until the like top of memory, and we were treating those as 4K blocks. And we built up this data structure, like in memory, actually, in that same memory, we built up a data structure that basically, as a linked list, said that all of these things are free pages. So these are the pages that we're going to actually use. We're going to use these divisions, which are 4K aligned. We're going to use these to actually this is where essentially where our address translation is going to point to. Is like we're going to take a page that we've allocated, we're going to have its physical address, and we're going to create a mapping to that page using virtual memory, and that's going to be how we couple these things up together. So let's actually go into this kvm init function and see how that works. I'm going to open that up here. We're in vm.c, virtual memory, not virtual machine. That is another VM. And this is quite a long file. There are under 500 lines of code, but there are quite a few things going on in here. We're not going to look at everything today because some of this stuff will make much more sense when we have a stronger grip on things like processes and kind of some of the other mechanisms that are at play with the scheduler and processes. So we'll get into that at that point. But we're going to look at how at least the kernel initializes its own page table because the kernel does translate addresses. We're going to see how that actually looks and works. And I guess we'll talk a little bit about processes at some point because I think it will be interesting to get a slightly wider view on this outside of the kernel and see how things are working in that way. So what we can see is that we're assigning to this variable kernel page table. That's defined up here. So this is the kernel's page table. Great comment, says exactly what it does. And I'm going to go to this type here as well. So a page table is actually just a pointer to a uint64. That is what a page table is. So it's just a pointer to some uint64 in memory. So nothing special. A page table is just a pointer somewhere, which makes sense, right? And as we know, there are 512 page table entries. Okay, so that's our kernel page table. Let me get back to this point where we were. And we actually get to that by calling this function kvm make. So kernel virtual memory make. So the comment here tells us make a direct map page table for the kernel. So the interesting thing here is that we're actually going to make a page table that's going to be used by the kernel, but it's just going to essentially map virtual addresses to physical addresses. It's going to basically map physical addresses to physical addresses. So the addresses that we construct for virtual memory, they will actually map directly to physical memory. And you might think that that's completely pointless. Like, why wouldn't we just turn off virtual memory in the kernel? And what we'll see is that once we actually get into scheduling and how that works and how we go from user processes back into the kernel, out again, switching processes, you wouldn't actually have any moment or opportunity to turn things off and on. So it's essentially, given that the way that this works and the scheme of scheduling, you can't actually have translation off in the kernel and on in user. At least not in RISC-V. Maybe you can do it in other operating systems. Okay, so what do we do here? Well, first of all, we just create an internal variable for the kernel page table. So that's what this is here. Again, just a pointer to uint64. And we just allocate a page to this. So remember, kalloc, we looked at this in the previous episode. We're just allocating a 4K chunk of memory. So that's what we're doing here. We're getting this 4K chunk of memory. This returns us a void pointer, and we convert that to a pointer to a page table, essentially. So we're saying that, hey, this thing is a page table. So there we go. We've got a page table now. The first thing we do with it is we set memory to 0. So we set everything in the page table to 0, or 4K bytes. And we go through this process of calling this function kvmmap. So kvmmap is a void function that adds a mapping to the kernel page table. It's only used when we boot, so this is like a one-time procedure, just like some of the other stuff we've seen during this boot up procedure. These are functions that are only called during this process. Does not flush TLB or enable paging. So this is essentially a form of caching that is related to virtual memory and how that works in the hardware and everything, because as this tiniest little side note, because going into this is a rabbit hole, and I can maybe link some resources in the description if you really want to know much more deeply about this whole process and actually kind of how the bigger picture of all this stuff fits together with CPUs and architectures in modern processors and programming languages. I'll link a talk below which is really good. But fundamentally, the TLB is a little cache that's used because if you imagine that the processor has to translate addresses every single time memory is accessed, that's something that can take a really long time because it has to access memory. So it's this also a chicken and egg problem, but it's kind of this very, at least it sounds like it wouldn't be a very performant system to have to go and translate in hardware through some table in memory, which takes time. You know, accessing RAM takes actual time. The CPU is faster than RAM in most cases, so there is a latency there. So if every time you have to do, like go and change some address into another one, you have to go and do that as a memory lookup, that's going to take some time. So there is a cache called the TLB, which just is the translation look-aside buffer. So there is a little buffer on the side, a little cache, which we can go and look into and see if like the addresses that we're trying to translate are already kind of like there is a quick one-to-one mapping already in that cache. If there is, we don't have to do that whole process of going page table, page table, page table. Okay, this is my address. So that's great. That saves a lot of time. And enabling paging is literally just making sure that we write into that SATP register and that it says that we have a valid translation in there. So that's kind of what this function is doing. So I guess let's take a look. Well, first of all, let's see what we're passing in here. So we are apparently at this point, we're mapping the UART registers. So the UART, if you'll recall, it's our serial interface. It's how we get input into the kernel. It's how we put output to the screen. So we're translating that. So we pass in our page table, and you can see here that the second argument is a uint64. It's the virtual address. So the virtual address we're trying to translate is the UART, and the physical address, you can see that's the next one, the PA. That's also UART. So again, we're making a one-to-one mapping here. We're not trying to like create a different scheme of addresses here. We are actually mapping physical address to physical address, essentially. The size of the thing we're mapping is a full page, right? So we're just saying that there is a full page worth of stuff here to be mapped. And finally, we pass in some permissions at the end here. And the permissions, they're just those bits that we saw in the diagram over here. They're these bits essentially. So they're going to be at least the read, write, execute kind of permission. So that's what we're passing in at this point. Okay, so in this case, we're saying that the UART registers, they are readable and they are writable. They're not executable. We can't execute code from here, which is a good thing because why would you want to? But that is a possible place that your system might be attacked. So if you think about, the perspective of a hacker, if they could somehow force code execution to happen from your UART registers, they might be able to do something kind of dodgy. Okay, so let's have a look into this function with that in mind. And what I might do here is just let's take a look here. So we've already read the comment. We don't do any any of that kind of stuff. All we end up doing is calling into another function that basically takes in the exact same arguments. This time it returns a value. So presumably it tells us whether this was successful or if it failed. And if it fails, we panic with kvm map. So there is this map pages function. Let's go to that one. It's just below, so let's scroll down. This one says create page table entries for virtual addresses starting at VA, the virtual address, that refer to the physical addresses starting at PA. VA and size, so that's VA and size here, might not be page aligned. So that's kind of interesting. Like we might be trying to map something that is not aligned on a page boundary, and that's going to be important. So that's something to know about the possible inputs to this function, right? We can't control that. We can't error out on that or tell the user that they have to page align. We can only put that in the comment. It returns 0 if it succeeds, -1 if the walk function couldn't allocate a needed page table page. So none of that's going to make much sense, I think, or at least not totally. And it hopefully will by the end of us going through this. So the first things first, there are a couple of variables that are just kind of set up and initialized. So there is a variable called A, fantastic name, could be anything. And there's one called last. And then we have a pointer to a page table entry. And as we can see, if we hover over here, a page table entry is just a uint64. And you might think, why don't we just, for all of these things like a page table, like this page table T and a PTE-T, why don't we actually just call them what they are? Why don't we say it's a uint64 pointer or a uint64? Well, the answer there is, of course, that this operating system can be ported to multiple architectures. So we would want to have the idea of a page table in all of those. We probably want to have the idea of a page table entry in all of those, but they might differ in, the width of the bits, right? For a 32-bit system, a uint64 is not what you're going to have. So at least even between RISC-V, you might want to have something more portable. So that's why we don't just say uint64 in those places. Okay, so we've got those. We don't know what they do yet, but we know that they're going to be used for something. Then we check that the size is not 0. If the size were 0, and remember we have unsigned values here, right? So they can't have negative numbers. So if the size that we're trying to deal with here is 0, that's not valid. Something went wrong, let's panic. Otherwise, what we do is we take the address, or we take A, and we say that A, the address, is our virtual address, rounded down to the nearest page boundary. So we looked at these PG round down and PG round up macros in the previous episode. You can see that basically it looks like this when we translate it. This is the macro up here, and this is how it looks after having gone through expansion. So basically what we're doing is, if we happen to not be on a boundary, we're rounding down to the nearest one. And the idea here is that we're going to basically try to make sure that we can create a proper page table for this thing, and it has to be on the boundary. So we allow the address to be translated somewhere in between, but if we're going to create a page table for it, we need it to be on the boundary. All right, and then we have this last, and the last is going to be the last address we're dealing with. So remember, these are virtual addresses. So this is the starting virtual address that we need to perform mapping for. And this is the final virtual address. And we get that by taking our virtual address plus the size -1. Then we round that down, and that's going to give us the actual sort of last page aligned boundary. Hope that makes some sense. It's going to give us the last place on a page aligned boundary that we need to get, because we can only allocate pages. So we're jumping page to page to page here. So this is the start address. This is the end address. So for an infinite loop, while true, what we do is we say walk the page table. So we're going to see what this does in a minute. But basically, this is us going through our page table, trying to find something at this address. And if we are we're trying to assign that to this variable here, PTE, right? It's our page table entry. If this returns 0, then return -1. And if you can see up here that -1 means walk couldn't allocate a page table page. So if we got 0 here, that means that operation did not succeed. But if it did, that means that PTE now refers to a pointer to a page table entry. And the page table entry is essentially the page table that we've allocated for this. I'm using the word page table, a page table entry, a whole bunch here. And I realized that. And you know what it actually may be useful for us to do in this is to actually step through this function with the debugger. Someone mentioned that it probably would be more useful to do that. Let's actually do that. So I'm going to put a breakpoint down here. And I'm going to start the debugger already. And it's not going to find anything yet because we don't have something to connect to. I'm going to run make qemu gdb. And that for some reason doesn't work the first time. You have to run it twice. I don't know why. But then we actually are now inside the debugger. Here. So let's take a look, right? We've got, if we add here VA, and we try, unfortunately that doesn't work. Okay, so we've got this value here, copy value, and let's just have something open here where we can like get these in a nice format. So this is the UR register address, you can see, that's just hexamillion. So that's the VA. The size we're trying to map is 4K. All of these things make sense. The physical address that we're trying to map to is the same. And when we actually scroll down here, we try to do our page round down. If we look at A, well, A is actually already aligned, right? Because this is already aligned on a 4K boundary. So if you think of it, 4K in hex is 1000 hex. That gives you a sense of if it's aligned. And aligned essentially means that it can be cleanly divided into that size. So in this case, it's already aligned. And our last address, well, our last address would be this one here. So it's VA size -1. Apparently we can't we can't actually evaluate that here. Yeah, I guess that the actual debugging environment between the virtual machine and VS Code is not that super well integrated, but essentially you can imagine that that is going to be this value plus 4K -1. So we're going to try to go to this this address, and if we round that down, that's going to come out to this value, which you can see is a little bit different, right? It's actually, where's the difference here? So that's 26843, and this is 268435435. Are they the same? Is this equal to this? Okay, so yeah, the first page and the last page are the same. And of course that makes sense now I think about it out loud, because we're doing one page here. So of course the first page and the last page are going to be the same. So all right, so good to see that working out. Then we're going to go down into this walk function. So we're going to see, does this work? And the walk function, we're passing in the page table, the starting address, and this value 1. So the page table, walk, it actually, we have a comment here, and it's taking in a page table, a virtual address, and a value, an integer value called alloc. So in this case, this is just going to be a Boolean value, like true or false. Are we allowed to allocate while we're calling this function? So the comment here says, return the address of the PTE in the page table, page table, so that's this variable, that corresponds to the virtual address VA. If alloc is not 1, if it's 0, then create any page table pages that are required. So the idea here is going to be that if during the process of us trying to create this page table mapping, that we end up kind of walking through the page table, and walking just means going from the next one to the next one, if we find out that this thing is not valid, the thing that we're pointing at over here is not valid, we're just going to create a page table here, and we are going to set it up so that it is valid. So the RISC-V SV39 scheme has a 3-level page table. The page table page contains 512 64-bit page table entries. A 64-bit virtual address is split up into 5 fields. These bits from 63 down to 39 must be 0. From 38 to 30 is a 9-bit index, level 2. It's called the level 2 index. 29 down to 21 is the level 1 index, and 20 down to 12 is the level 0 index. And then finally, those last 12 bits that we have, those are the offset within the page. So, all right, keep all that in mind. So first of all, is this virtual address like greater than the greatest possible virtual address? This is actually a macro that's defined here in RISC-V.h. And you can see it says 1 beyond the highest possible virtual address. Max VA is actually 1 bit less than the maximum allowed SV39 to avoid having to sign extend the virtual addresses that have the high bit set. So there's just a bit of detail that I would say don't even worry about for now. This is essentially how we compute the largest virtual address. And you can see we've got here the 3 levels of page table index plus the virtual plus the offset. So that's just that number minus 1 shifted, a 1 shifted up by that number, which is tells us the last possible address. You can play around with that if you would like, but essentially what we're going to do here is to see that it doesn't exceed that, of course. Then we go into a for loop where we start our level at 2, and that's the level of the level 2 index, level 1 index. While we have a level that's greater than 0, we're going to decrement the level and do this stuff. So first of all, what do? We look inside our page table using our level and our virtual address to figure out which index we're looking at, right? And then we grab the address of that. That's a lot to take in. Essentially, we're looking up, using our virtual address now, we're looking up into our page table, and that's going to give us a page table entry. And we use this px macro to do that. So the px macro, what that actually does is it is going to grab that that offset for us. So let's just go back to the spec for a second, because otherwise it's going to be a little bit tricky to think about this. This is our virtual address, right? So say we wanted virtual address level 2, which we do in this case. We want to isolate these 9 bits up here. So basically, if we go back to the code, what the code is doing in this case is it's taking our virtual address and it's shifting it down by a value here called px shift. So if we look at that, that's just above. That is the page table shift, 12 bits, plus 9 multiplied by the level. Again, don't worry too much about this. It's a lot of math. You kind of need to work through it and kind of go through it on some addresses. But if you think about what it's going to do, it's going to take this part and shift it all the way down so that we just have these 9 bits. And then at the end, you can see that it does a masking operation. It masks it with the px mask, which is just 9 bits. And that is going to give us those 9 bits. So great. So that's going to give us an entry into this page table. So what do we get from that? We get this PTE. And you can see that PTE points at, well, this is the address, but the thing at PTE, if we look inside PTE, it's got the value 0. And when we look inside a page table, we're looking for one of these entries, right? So we're looking for one of these page table entries. And remember over here we have a valid bit. So just the least significant bit, it should be a 1 if this is an actual page table entry. If it's not, then we know that this whole thing isn't valid. So going back to the code then, the first thing that we do is we look inside this pointer, we look at the value inside, right? Which we can see is 0, and we AND it with PTEV, the valid bit, and that tells us, is this page valid or not? If it is valid, then we actually set our page table to a translation of the page table entry to a physical address, because every page table entry can be translated to a physical address. Again, if we go back to that diagram in the spec, this is what we have inside a page table entry. Well, these three values here, we can use those to create a physical address that this points at. So, in this case, we are absolutely not valid, right? We've got 0 inside this thing, so we don't have a valid page table. And that, of course, makes sense because we haven't done any setup yet. We're in the process of setting this thing up. So if we're not allowed to allocate, or the allocation doesn't succeed, so we're just going to try and grab a page here. As you can see, we're calling kalloc. We would return 0 at this point. But at this point, it's both we can allocate and we should be able to assign ourselves a page. We get ourselves a page in the page table, so we've already set our next level of the page table to this. And think about what we're doing here, of course, right? Is we're starting at this point, and we've just gone and found whatever we're pointing out at this next level, figured out that this one was not valid, so we've assigned an entire page to this 4K, which is all 512 of these 64-bit integers. And we are now going to deal with what this piece of memory that we have now. So what we do is we set everything to 0, and then we set that very first page table entry, which is, is this one, page table 0. We set that one to be a physical address translated to a page table entry. So basically we turn a physical address into one of these entries, and then we set the valid bit. So riding back over to the spec, we somehow take our physical address, we chop it up, we shift it up into this position, and then everything else would be set to 0 in these parts. And now we're just going to set this one bit over here to a 1, so that we know that this page table entry is valid. So now, from there, we've actually created ourselves a valid page here, right? None of the other pages are valid, everything else is 0, but this page is valid. Okay, so then what we do is we use this macro, and so we talked about this PTE to physical address, and now we've got a physical address to PTE. Well, let's just take a little look at that. It's another macro defined in this RISC-V file. So this one takes our physical address, converts it to a UN64, shifts it down by 12. We chop off those 12 bits that are our page offset, because again, we're dealing with a page, we're not dealing with each value inside a page. Then we shift them up by 10 bits. Why 10 bits? Well, if you look at the spec, you'll see that if we, the beginning of this physical address thing here starts at bit 10. So that's why we shift up by 10 bits, because we're leaving ourselves a bunch of space here at the bottom for these values, right? RSW and all of these ones. All right, hope you're with me so far. All we've done is just sort of made ourselves a valid page table at this point. We've allocated the memory. We've set up that very first page to say that this page is valid. And during the process, we actually assigned our new page table. So this is now the place we're going to start looking stuff up. All right, this is our new page table. Previously, we were working from like this point. Now we're going to sort of say that for the next thing we look up, we're going to be here. So we're going to come back up to this point. We're going to loop back to the top of this loop, and we're going to say, hey, then our level, of course, is going down. So now we're looking at level 1. So now we're looking at this page table, and we're going to go and track down exactly which entry we're looking at this page table. Like, is it down here? Is it up here? And we're going to look at that one, and we're going to say, is that one valid? Well, of course, it's not going to be valid. So let's go through that. We're now going to the next level of page table. Of course, it's not valid. So we allocate a page again. We set all of its memory to 0, and we set the first entry in that to be valid. So think about it. Maybe we were here. We found this page table. We allocated it. We set this one to valid. And And then finally, we're on the final level. So we come back, and actually we were able to assign that page table entry. So this is now our page table entry. So if we look at this one, how do we do this? They say that this is a uint64t pointer, this address. That's not what I was looking for specifically there. Our address is page table, this one. uint64t pointer, this address, no symbol uint64 because we don't use the t part here. Okay, so then that whole thing actually, we need to, yeah, so what we get from that is this, this value. And if we copy that value, well, if we look at the very first bit, that bit is set, that's a 1. And if we shift this whole thing down by 12 bits, we get this. And if we then shift the whole thing back up by 12 bits, we would get this. And what does that look like in hex? That is, well, actually, it's not going to completely look right because there are some, it doesn't actually completely work in this way. But in any case, this is now a valid page. Okay, so now that this is all working nicely, we've grabbed ourselves a page table entry. It should be valid at this point, so let's check it is valid. So what we do is we're now going to write into this page table entry, and it already contains, it still contains, wait, how does that make sense? So we walk to the page table, so we got our page table. The thing inside the page table entry is not valid, of course, because now, sorry, I've actually made a little bit of a thing here. Like what we've done is we've gone through these levels and we've gotten to this last level, and kind of the last level points at something, some physical memory, but we haven't assigned that last level. So that's what this part is now doing. So it's now saying, okay, we got the last entry in the page table. So we've gone through 3 levels of translation. And at this point, we're actually going to say, take the physical address that we're interested in. So this is going to be our hex 1 million. Add in the permissions that we're interested in. So we said in this case, let's take a look, kvm make. We said we were interested in read and write. So let's try to get back to where we were. That's the easiest ways to do this. So we're going to take the permissions, the read and write permissions and the valid permission, and we're going to use all of that to create a page table entry. So this is our page table entry here, which I guess we can sort of look at in binary. That's of course not going to work. Copy value. So in binary, we've got these bottom 3 bits set. And if we look in the spec, of course, that is the valid bit, the read bit, and the write bit. We don't have the execute bit set. We don't have any of these other bits set. And by bit 10, we should be getting to a physical address. So that's kind of what we would see over here, except you can see that it doesn't quite look like that. You can see that like kind of the pieces are shifted around a bit. So yeah, so we don't see like the bottom pieces of any address here because they're all zeros. No, it should make sense. Okay, so finally we check if we're at the end. So like, is the current address of the current page that we're looking at equal to the last one? Well, of course it is, right? Because this is the final page table. So we're done here. We did our mapping of the UR. All right, so that's how that whole thing works. It's quite it is quite a lot to wrap your mind around. But essentially what we've done is to build this structure, right? We've kind of said that, and of course we don't have the SATP register set up yet, but we've just built inside memory, we've built some of these page tables using this page table that we have here. So we've got a base table, and we've used that with indexes that will basically figure out how to go and get the correct place. We've got now this page table. So this is the one that's our key to all of these other mappings that we've made. So then we go through and we do the same thing for a bunch of other places. So we do the same mapping for something called the vert.io interface with the same kind of permissions. So I'm not going to go all the way through that now. Let's take the... we actually have breakpoints there? I don't, but let's just pop back out of that function. Up one. Yeah, so then we do this one for the plick. This one you can see that we're actually allocating quite a lot more pages here. So this one actually has to go through and not only do 4K, but I think, what is this, like a hex 40 times 4K? Well, I'm not exactly sure what the division there is, but yeah, quite a lot more, right? So we're not done once we go through once in the loop. So we need to go through a bunch in this case. All right, so we're going to step over that. Then we get the kernel base. So this is actually just us mapping the rest of the kernel code. So we need to be able to map all of the kernel's internal code and everything. So that's what we're doing here. And of course that we have to actually work out how much code there is in order to do that. So we get the symbol eText. The eText symbol comes from the linker script. You can see here that we have in the linker script, we provide our text section, which starts at this address and includes all the code, something called the trampoline, does some alignment, and eventually gives us this symbol eText, which is the last address there. So we use that symbol eText to figure out like where we are in relation to the base kernel, which is just at hex 8 million. And we say that all of that stuff is readable and executable, but not writable, of course, right? Because we don't want people to be able to change, or us even in the kernel, we don't want to change the kernel code at runtime, because that would be bad, right? You want to make sure the kernel has been coded ahead of time. So we do that. Then we go to map in physical data, so the rest of physical RAM. So this is all of the pages actually that we have in our allocator. So we're going to take all of those and give those read and write permissions. So not executable, but everything there is just readable and writable. Kernel data, wait, so this goes from eText to eText and everything up until that. Yeah, so everything from eText. Oh wait, everything from eText. So if we actually go back to the linker script here, eText is here, and then all of this stuff, so the read-only data, the BSS, everything up until that, up until the end of memory actually, all of that stuff gets mapped to read and write. So we can read and write it. And I guess if we need to set something up as executable when we have a user process, we're going to set that permission explicitly. We're not going to do any of that kind of stuff now because we don't want to make anything executable that shouldn't be executable ahead of time. Now, finally, we're going to get through this. And finally, we come to allocate something called the trampoline. The trampoline is an incredible construction in this operating system, which we're not going to talk about today because I think we're going to need to dedicate ourselves a little bit of time to talk exactly about how we end up getting from the kernel into the user code and from the user code into the kernel. The trampoline is a really super smart procedure that is used to make that happen. And what you can see is that this is the one place where we don't map the same address twice, right? Everything else, UART, vert.io, plick, kernbase, eText. In this case, we go from the trampoline, which is this computed address, which is in fact the very last page. We map that page to something called trampoline here, right? Which is actually, if we look at where this is defined, well, we can see that there is an external symbol trampoline, and then if we open this trampoline.s file, well, inside this this assembly file, in fact, there is a symbol called trampoline, and it is in fact just this piece of code, right? So you can see that there's a piece of code here that runs that has to be written in assembly. So that's what exists here at this trampoline address. So we map the trampoline address, which we say is the very last page of memory, we map it to that area, and we mark that as readable and executable because we're going to execute some code from there. And then finally, after we've done all of that, we call this function called prop map stacks. So allocate and map a kernel stack for each process. So we take our kernel page table. Let's go inside this function. So the actual idea that we're going to do here is that in xv6 there are a fixed number of processes that can run, right? There is a maximum number of processes. We can take a look in the parameter.h. The number of processes in the system maximum is 64. And the pretty cool and interesting thing that we do there is that we allocate all the memory, and like that number is fixed. Like we'll always have resources for 64 processes at all times. That's just something that is done for like making things easier. You don't have to do things that way. Of course, it would be a bit wasteful to do that, especially in modern systems where you're going to actually have many processes. So you don't necessarily want to, constrict a system which may have many processes or may have a few. You kind of want to dictate the way that will run. But in this case, in xv6, everything is marked out ahead of time. And what we actually end up doing is we take one of these proc structures. So I'm just going to go to the definition here. This is the structure for a process. And there's quite a lot going on here. And of course, we're not talking about processes today. But there is this whole structure. And there is an array here called proc. This is in proc.c. There is an array of these structures for 64 of them. And like that just exists. That exists in memory. 64 of these structures. So, funnily enough, this function actually lives in proc.c. I didn't notice that until just now, but this lives in proc.c. And what we actually do is we iterate through all of the processes. We allocate a page, and if we're not able to allocate the page, we panic at that point. But what we actually do is we're doing a virtual mapping here for the kernel stack. So something, and we'll get into this in a deeper detail later. I've said that a lot today, but there's going to be a lot to take in. The kernel actually, in the xv6 kernel, we have a kernel stack for every process. So this is kind of one of the interesting things, is that we think of like running code in the kernel and running code in the user process. We kind of think of that as like user code's running over there, and then there's this one big thing called the kernel. And that's not actually the case. It's kind of like you can almost think of there being 64 instances of kernel code running, one for every process. And when we come out of one process and back into the kernel, we're coming up in that process's context. So we're coming back up with a stack which is specific for that process. That's something that I didn't realize when I started studying this code base. I kind of had this conception that kernels there would be kind of one monolithic program running that is the kernel, and we would arrive back there sometimes from interrupts and things like that. But, everything would be kind of managed from one place. But actually, it's sort of like you can think of this whole bunch of parallel kernel threads running. So there's kind of a thread running for each process and a thread running for each kernel, which is related to that process. It's quite an interesting idea there. What we're doing here is we're giving ourselves a stack. We have to map that stack in terms of virtual memory. So there is this macro here that basically goes through and figures out where the kernel stacks are going to live. They do in fact live under the trampoline. So that's what we just talked about there, the trampoline page. And each is surrounded by invalid guard pages. So it's quite an interesting idea here that we shouldn't talk too much about, but there is this idea that we're going to actually set some pages to never ever be used. And the reason we don't use those pages is because we want the kernel stack to create an error if we ever try to, if we do a stack overflow or a stack underflow while in the kernel. Because what's going to happen is we're going to have this kernel stack for every process. and we call functions, and that's going to add things to the stack, and there are variables that add things to the stack. If we ever go over our stack size, we'll end up translating into an invalid page, and that invalid page will cause the CPU to take an exception, and we'll end up in an exception handler. So that's pretty cool. I mean, that would only happen in more extreme circumstances, but yeah, it's just something that's going to protect us in that way. So that's why that's done. We're not going to go too much into that now, but what we do is we end up figuring out what our address of our virtual address of our stack is, and we map that virtual address to the physical address of the page we just grabbed, and we say that it's a single page and that it's going to be read and write. So kind of at the end of that, we end up, let's see, can I get ourselves out of this? Seem to really be at the end of this. Yeah, for some reason I can't find my way, but I'm going to see if I can put a breakpoint down somewhere. Map pages. Map pages down here. Where are we? Where are we? Here we are. Okay. Not quite sure, but it seems that we've... Sometimes this kind of goes a little bit nuts. The debugger. That is kind of the nature of, like, you know, very low level debugging. Let's see. Yeah, unfortunately my breakpoint is just like lost to history. But I think if we look in the thing here, you can see that we actually sort of made it through. So, okay, so the idea here is that we've actually set up a page table for the kernel that is translating addresses like on a physical basis, right? So all the addresses are just the same, but they're going to go through this mechanism of the address translation. So then we've also allocated stacks and proper mapping for all of those stacks in the kernel for the kernel page table using this prop map stacks function. And then finally we return the page table, right? So remember, this is just a pointer. It's just a pointer to the place where a page table starts. So we return this, and that takes us back to this main function. Let's actually quit this out. So then we actually turn on paging. We turn on paging. So let's actually go into that function for a second. And you can see that we end up switch the hardware page table register to the kernel's page table and enable paging. So how does that work? What we end up doing is we do this thing called sfence VMA, and we've looked at fences before. At least we've looked at the idea of a fence. So if we're using like locking instructions, for instance, we want to use a fence to tell the CPU that it cannot reorder memory accesses beyond that fence, right? So the idea is that we have a lock, and that usually the CPU is free to kind of move things around within a certain range so that it can be more efficient about how it loads and stores from memory. Well, in this case, what we're doing with an sfence, which is a supervisor fence for virtual memory, we are saying that we're going to change the way that virtual memory works. So here's the beginning fence. So everything, all the memory accesses which were happening before the fence have to happen then. Then we're going to actually change the SATP register. And because of that, like if we had virtual memory running before and we had a page table, and the CPU was able to like reorder accesses, if we didn't do this, we might end up in this situation where a read that we expected to happen with one page table happens with the wrong page table, which would of course be completely catastrophic because they're not going to be the same memory at all. So we put a fence down that guards us as we change the page table. We have this macro here, make SATP. So if we just look in there, That basically takes our address, shifts it down by 12 because we don't need to talk about our 12-bit page offset, right? That's not needed, so we get rid of that. And then we use this thing SATP SV39, and this is basically the value 8 shifted up by 60 bits. Let's just go back to the spec for a second to see what that even means. Well, here we've got this mode field, and basically we've shifted our mode up to here, and I think somewhere here we can find ourselves a table, and it says what the various values in this table mean. So we put the number 8 in there, and that means that we're using a 39-bit virtual addressing scheme. So that just makes sure that everything that we're doing in the kernel and in the processor are actually aligned. Like, this is how we're going to do address translation. For instance, if we had 9 in there, that would tell us we were doing 48-bit address translation. If it was 0, that would be no address translation, right? So we would actually turn off address translation. We would be on a physical basis. And this is where we are before we do this, right? This register contains the value 0. So we're not doing any kind of memory paging, virtual memory mapping. So it's 0, but as soon as we set it to 8, then we immediately, from that moment, begin translating addresses. And it's such an interesting thing to think that, like, just before this thing runs, we're all on physical addresses. The second that we do this right, we're doing address translation. So all of that stuff with the page tables is now happening on this next instruction even. So we do a fence here just to make sure that this thing happens in isolation, that no other memory accesses happen before or after this that aren't like reordered. And then finally, we're done with that. So at that point, we would return and we would begin initializing the process table. So this has been a ton of information, a real ton of information. And I really do advise you, if you're following along with the series, you're enjoying it, just download the code, right? Get QEMU set up. Grab the Docker image so that you can actually compile all this stuff, or install the RISC-V toolchain yourself if you're feeling adventurous. Play around with this. Get the GDB part working so that you can step through the code and kind of take a look at this. Try and see if you can understand exactly what we just went through. See if you can make that make sense, because of course I can explain it to you now, but until you kind of work through the mechanics of it a little bit, it won't fully click. So maybe it did, and in that case that's great. I'm really glad. Please let me know in the comments if you're like, no, I got it immediately. I understand virtual memory right now. Otherwise, let me know in the comments if you've enjoyed this, if all of this has made sense. Of course, if you've got questions about this or something hasn't made sense, please let me know please just ask, and I'll try my best to let you know if I can. If you think I've missed something, you can also let me know in the comments. I'd love to hear it. And if you have any other kinds of ideas, or you just want to chat about something, maybe ask a question about something in the future, yeah, you know where you can do it. You can also visit the Discord server for the Low Byte Productions YouTube channel. I'm usually on there and can respond pretty quickly. Okay, so that's it for virtual memory. This is like, this is a big milestone kind of in the understanding of the operating system, because virtual memory it's a big thing, right? And now that we understand this, we can build on top of that. So you can see, right, we got ourselves the allocator, the page allocator, and that became a component in our system that we used in the virtual memory setup to kind of like bootstrap. Now, like, we've got this other tool, we can start using it, right, we're bootstrapping. So now from this point, we can actually start building on the idea of user processes, and that's going to be incredibly interesting. So I'm going to have a think about how we're going to tackle this next part, because I'm thinking we've probably got enough information, probably enough understanding to start thinking about how the scheduler works. And that is probably the biggest thing in this whole project that's takes a bit to understand. And when you have those concepts, virtual memory, the idea of memory mapped I/O, all of that like base level stuff, how the CPU operates, registers, when you then have the idea of process scheduling, you have all of like the biggest key components of an operating system, and you're well on your way to kind of like picking up bigger projects, more advanced things, and kind of being able to hack on them. So I'm really looking forward to that. I hope you are too. Take it easy, and I'll see you in the next one.